In problem 37, we're trying to find the mass of the atmosphere above the Earth, atmosphere, up to 100 meters high. How in the world can we find the mass of the atmosphere? Well, we have to simplify things. We have to assume the Earth is a perfect sphere, right? Ignore mountains, ignore valleys, ignore that person standing over there. Actually, even if you ignore mountains and valleys, the Earth is actually not quite a perfect sphere still. I think because of the rotation, it's like a little wider around the equator than it is from the North to South Pole. Ignore it. What we also have to do to actually get an answer is we need to assume that the density just depends on the height above the surface of the Earth. It's a function of h, the height above the surface of the Earth. We have to assume this has got a simple formula for the entire Earth. That's not reality either, right? Weather affects things. High and low pressure, you heard of that before? High and low pressure affects things. So this is an oversimplification as well. One formula for the entire Earth, and the formula given in the book is 1.28 e to the negative 0.000124 h, and the units are kilograms per cubic meter. H is in meters. It's a volume density. Notice it's exponential decay. So as you go higher, as h gets bigger, the density definitely gets smaller. You might say pretty rapidly because it's exponential decay, although that coefficient is very close to zero. If you are at sea level, h equals 0, the density would be 1.28 kilograms per cubic meter. Imagine a cubic meter of air, like, okay, it's big, something like that. Its mass is supposed to be about 1.28 kilograms. Is that right? I have no reason to assume it's wrong or bad. What would it be at the top of Mount Everest? Mount Everest is 29,000 something feet high, 9,000 something meters high. I don't know, 9,500 or something. I might be wrong. 0.394 kilograms per square cubic meter. About 30.8% of the density at sea level. Yeah, you can't breathe up there, right? That's the death zone. Or you can breathe up there for a short while, but you'll die after a couple hours unless you got oxygen. So, okay, no reason to assume this is wrong. Let's just assume it's right. How do I use this to figure out then the mass of the first 100 meters of air above the surface of the Earth? It's constant along for constant values of h. I guess we'd have to slice thin slices of the atmosphere at approximately constant values of h. Well, what kind of object would result? Thin, hollow balls would result, right? The Earth itself, I should probably use blue for the Earth, right? The Earth itself is the sphere, the ball part on the outside and the inside for the interior of the Earth. And then above the Earth, we got the atmosphere, and we're slicing it with thin slices at approximately constant values of h. The resulting objects would be thin, hollow balls, spheres with a tiny amount of thickness to them. Dare I draw such a thing? I don't think so. Not when I've already drawn the Earth. I think I probably should not try drawing that. If we multiply delta of h times the approximate volume of the thin, hollow ball, that would give us the approximate mass of that thin hollow ball. Add those up to get the total mass. Yeah, let delta H go to 0. We're going to get an integral. Delta V, the approximate volume of the thin hollow ball. Now, technically, so imagine the thin hollow ball as being made up of, you got an outer sphere and an inner sphere. That volume technically should be the volume of the outer sphere minus the volume of the inner sphere. But maybe we should do the cutting again to keep things simpler. Cut the sphere somehow and unroll it. What we would get if we flattened it without changing its area. Would we get a disc, a circle? Seems reasonable if we cut it appropriately. Let's pretend we do. The sides would not be vertical. They'd be slanted because the outer sphere has a bigger surface area than the inner sphere does. But pretend. I better not try to draw it. Well, I mean, I guess I could kind of draw that one. It's like a thin disc. The width would be delta H. And what's the area? How about the surface area of the entire sphere? I didn't deform it in area. Somehow I deformed it from a sphere to a circle, but pretend I didn't change the area. It's all in your mind. Area of a sphere, not pi r squared, but 4 pi r squared. What should I use for r? I'll just call it r and not worry about it at the moment. This would be approximately the surface area of the sphere times the little width. Okay, but maybe now I need to worry about what r is. What is r? Remember, this is a thin slice of the atmosphere, h meters above the surface of the Earth. The radius is the distance from the center of the Earth to there. H plus the radius of the Earth. What's the radius of the Earth? According to the book, it's 6,400 kilometers. 6.4 million meters. So I guess R becomes 6.4 million meters plus H. To find the total mass, then, multiply that by delta of H. We get 4 pi delta of H times 6.4 million plus H squared times delta of H. Add those up, let delta H go to 0 to get the total mass. As an integral, it'll be an integral of this function, 4 pi delta of H, 6.4 million plus H squared dH. I want the first 100 meters, so H goes from 0 to 100. That should be the mass of the first 100 meters of the atmosphere. Delta of H, 1.28 e to the negative 0.000124 H. I'm integrating 0 to 100, 4 pi times delta of H times 6.4 million plus H, quantity squared dH. 6.55 times 10 to the 16th kilograms. You can write that down. I'm not going to write it down. 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion, 10 to the 15th is a quadrillion. This would be about 65 quadrillion kilograms. Right? How much more is that than what your mass is? Well, or my mass. What's my mass? I figured it out in kilograms recently, but I forgot. I think I'm around 75 kilograms. It's about 873 trillion times more than my mass. Okay. Imagine 873 trillion copies of me. That's the mass of that first 100 meters of the atmosphere. 873 trillion copies of me would fill up practically every square meter of land.